So, I just wanted to make a small video, maybe because I was missing from posting anything on my YouTube for a long time, and it was just a small rant or just some news and some videos I have seen and articles and could be code rant. It didn't fit in Optimosophy as I'm not presenting something on my own. I know I have OptiRants, but it's about game runs. I have some random runs there. It doesn't fit in anything. Some Optimong, some old political runs, maybe cultural runs, and maybe I don't want to do this anymore. And I'm just running something in the background to have something, and it's gonna be a small video, just saying few things. First of all, what is this? This is a Virtual Boy emulator. This is my Starfield on the Virtual Boy. I got a Virtual Boy. I was supposed to code stuff for 3DO. I want to go back to 3DO, but then I started playing with other things. And this is with red and blue, for red and blue glasses is this emulator. No, it's not that. You could disable it, maybe. Oh, now it's disabled. What the hell? Ah, there it is. There are still some red stars. That thing doesn't work. I don't know. This looks better in the real Virtual Boy because I recently got a Virtual Boy and started some experiments. Although for some reason this CVB, if you try to compile with anything more than no optimization, if you want to enable the optimization, it gets linear errors, and I need to see that with the community. And there are some other solutions, but I couldn't make them work. So at least for testing for start, that was good. Because I got a Virtual Boy. Meanwhile, I'm not going to show you something now, maybe in the future. The last 2 weeks I started with new platforms that I haven't worked before. I have an Amiga 1200 with 030 accelerator, and maybe run this to have some darker screen. What the hell? And as long as I talk, and I got hooked. It was Amiga. Looking at some Amiga coding tutorials on the internet from Photon of Scoopex first, and I used ASM1 and started learning 68,000 assembly, which is really good. It's a really good processor. I really like it now. I had to get used to different notation, like the source being first and the destination second in the opcodes and other stuff. But I was missing something from my life. And also the Amiga with the copper chip. I had just tried the copper and tried to write something in the first bit plane. Tried to do this star 3D stars is ported from the Amiga stars. And I also did that on the Atari ST. Because then I went to my Atari ST and tried to code something there on 68,000 from another tutorial. So I'm both into Amiga and Atari right now. And I'm really into it, and maybe you will see some demo in the future on those machines. And bit planes are very interesting because there are so many potential for optimize. I mean, it makes things slower, but there are so many potential, so much. If you like that kind of stuff, if it's like a riddle, how can I write things in unique ways? Not a generic chunky to planner, because that will be slow, but some other ways depending on the effect to gain that speed. And ideas are already popping in my mind, but I have to try them. And also in the Amiga, specifically with the copper and the blitter chip, you can do a lot of I started watching on my real Amiga, and I also got an Amiga 500 recently. I bought a second one to be able to watch the demos. And now I got some demos and I have more context. Like, oh, they do this using the copper. Previously it was like, oh, that's a nice whatever effect. But now I think, oh, that's not just software rendering on the bit planes. It's using the copper in that way compared to a pattern that it was created previously on the bit planes. And there is more to see. But anyway, that was 2 weeks ago, and then I got my Virtual Boy card with my Virtual Boy and started trying things here. And this thing on the real thing, because the stars are small, you barely see the red dots, but if you see them, they are magical. And the 3D, I made the 3D sense work with some parallax based on the distance. And it's really there, but it's just that the screen in the Virtual Boy is far away. There is border. You don't feel like you are inside the stars, but you feel the depth of the stars at least. I might later try to write a polygon rasterizer. I'm just rendering on the videoram. I haven't used the background or sprite that are consist from tiles. The videoram is not consisting of tiles. I thought it would consist from tiles too, but it's 2 bits per pixel, and it has a as you go serially, it goes vertically up to down from left to right. Anyway, I just wanted to make a random window, and now maybe I'll go to the main thing I was talking here. Here are my stuff I was looking. I really need to go back with some OptiNews or something and work back on some 3DO project. Anyway, I was looking at, I have the game Rants, I call them Rants. It says Rants. So this is for game, and a lot of this video are a bit horrible, to be honest. And then I have some Optimonk Rants, but nothing fits Optimosophy. That could be an Optimosophy thing, but I'm not going to code something. So anyway, the thing I wanted to say, maybe look this YouTube channel. I knew this YouTube channel because the author of this channel was made Handmade Hero. He was going, but this is 667. I never watched most of them. They are too big. You have to. I lost the time when it started, and I was like, no, I have to see 600 hours of. Also, they are interesting. I could have watched specific episodes. I got recently attracted to his site because, first of all, I have seen this video. He's also into the idea that we are wasting a lot of cycles in modern computers and we don't realize something that it's also interesting to me. And he make a video, he has made videos like that before, where he looks at some aspects of the clean programming, like, some modern object-oriented programming practices that everybody says it's good, you should do everything like that, but how this affects performance. And he has some examples here. But later, I have seen that one. So this is like a stupid...
I used the latest frameworks. Followed all the advice on Stack Overflow.
I'm not gonna show it. So this was like a fun invitation to his new series of videos, which are here. Now, I have to say, unfortunately, you have to pay for a subscription. But because I'm really interested in the subject, and I'm really interested in the philosophy of optimize from many aspects, even the rants, even if some of the things I'm looking at this show, They are familiar things, but there are things to learn, and I'm curious about how much is wasted because I haven't done it. And okay, it's here. And for example, the waste was I have it here, an interesting video. Unfortunately, these are not public, as I said. You have to pay for a subscription. There are a lot of people who did, like $9 a month, I think, and I did it too. But it shows how you start, how a simple addition in Python compared to a SQL, how much more cycles is wasting, because okay, the Python is an interpreter, and while in assembly language an add would be one command, here it's done with the load effective address, but it could also be an add EAX, EBX or something. One instruction, okay, it shows you the scale, something that most people don't recognize. And even I have not thought how much is wasted from this to the script language we use and all the boilerplate we have above, or the layers above layers above layers. How much? He's claiming that in some cases it could be 1,000 times more. And I'm like, isn't that too much? And then in a way, it gets there. Because the Python interpreter for the same command is doing this whole thing. Because it's not just doing the add, it's running the interpreter, which does various things. Like 181 instructions. And some of the instructions might be slower than an add or lee instruction. And then he goes the other way around and says how on the C side, on the C++ side, if you do an add, I don't know if it's here. Maybe it's okay. It's in the later examples. He is using the when an instruction can when a CPU can run more than one instructions per cycle, depending on how you arrange your code. And doing it with, I mean, it's a very simplex. It's just an add. It's not necessary, but it's like theoretically where we can go using simd for that. He has basic. This is a nice set of chapters because it goes through every aspect. Multi-threading, and it ends up. Then it even gets to Python. There are some methods to, if you want to write Python or whatever, you could still be performance aware, and there are ways to run C code from Python or some better libraries to do the additions, the sums for you. So there are workarounds to not be that slow, to be faster. If you just don't want to touch C or other languages. Because it's not about C or Python, it's about the mindset. This is what I want to talk about again. And now, it goes later. This is the free bonus post on YouTube that you don't have to pay. Unfortunately, he turned off the comments, and many people have criticized that. Also here, if you click here, there are comments here. I don't know why there are so many airplanes. And I'm in this part for some reason, and maybe that's good, to get people into the old mindset and understand, because we have forgotten how processors really work. There are some chapters in the old 8086, and it shows you how the instructions were decoded. I think it's really good. I mean, I know some of that stuff, but there are a lot of stuff I haven't thought. So, and he also put some exercises to the viewers. If you want to make an emulator that just decodes the instruction add ax, comma bx, comma cx, comma all the add, like a simple, it goes. And some people are responding, yeah, I made it here in this language, that language, in whatever language you want. I think it's a really, I don't know, yeah, I don't know what the future chapters will have. But anyway, I really enjoy this series. It's unfortunate. I mean, all good thing that you have to pay a subscription for others who would want and wouldn't want to pay. And that was the thing I wanted to say. And I might go. I might say one more. I mean, I might just run, not in a negative way. I might just what this whole thing means to me. When I most people, when in our modern computers, when things go so slow, and when you are used to machines with 4 gigahertz and 4 gigabytes of RAM, 16 gigabytes of RAM or whatever, and you have some basic GUI element that slows down or something, you don't realize it. You think, okay, computers are so much fast. That's the speed that the modern computer has. So if I tell you, I have a Raspberry Pi, the first Raspberry Pi had, I think, 600 megahertz ARM processor and maybe 512 megabyte of RAM, maybe 256. You could be like, you will extrapolate that if my modern 3.4 gigahertz computer, I think mine is 3.4 with, I don't know, 8 cores or maybe 4. I don't know, it doesn't matter. It's too much. If it struggles with what would that Raspberry Pi do? And people will say it's too slow. And when I tried, there was, I think it was Raspbian, there was a Debian, and it has, of course, because I'm not familiar with Linux, I didn't know what to do on the command line UI, and maybe that's better for that. I ran the user interface, which there are different user interfaces. I don't remember which one they had installed, and it was the most unresponsive thing I had ever seen. And you think, yeah, 500 megahertz is not enough for operating system UI. You would think, people would think like that, because they think I have a 4 gigahertz machine and things struggle sometimes. So why wouldn't the 8 times slower start? This is what they think. But then you go to Amstrad CPC and there is SimPOS, an operating system on a Z80 of 4 MHz and 128K RAM. And if people would see that, if I told them there is an operating system there, they would say, you are hoaxing us. Okay, you are a faker. This is impossible. It's like you are telling me you have traveled 1,000 times the speed of light. This is physically impossible. That's the thing. When things are so slow in modern pieces, you think that's the best. That's the speed computers have. But if you go the other way, if you see what people did in the demo scene on the Amstrad CPC, on the Amiga, and even serious programs, applications, games, utilities, with some of them had UIs, and they were responding okay. And especially if you code for the old platform and try to push it, your first attempt will be very, very, very slow. You will think it's impossible. How do they even do anything in those computers? How do they even do anything? But if you push it, your mind expands. My mind have expanded all these years by retro coding. Not just because, but writing something that is a slideshow and then make it run 50 frames, being able to slowly increase. And that's the other thing. There is no. There was a chapter of Michael Labras. That's also a point I'm going to do. We'll go there, but let's see. So there is another well-respected developer who has written a book called Clean Code, I think. He's called Uncle Bob. I remember this guy. I remember because he had some kind of controversy where he was accused of misogyny. Even if he was praising women, he was saying we did a lot of bad things to you, but he said it in a way. So I think the controversy was bullshit, and that's why I started following him at the time. But that's out of the thing. Uncle Bob is famous for his clean code website and book. Now I'm not much into this clean code code design thing, so I'm not familiar, and I'm not. I like to write algorithms. I like to write algorithms not optimize. I like give me a simple language. I don't like the. I'm not going to criticize. I'm gonna say that this thing they started the discussion. I'm not gonna read all of it. Casey Muratori, who did the clean code horrible programming, horrible performance, sorry, and Uncle Bob, they started the discussion about this thing, like you have misunderstood clean code. No, here is the problem. Most of it is, and maybe this is updated. And my opinion about that is there are programming dogmas. Like you should code only like this or only like this. This is the thing that closes the mind. And sometimes, in my side of things, when I try to optimize, I might write things that are considered horrible code. Especially in the old platform, you have to do things that are considered unreadable, and I think people find very easily things unreadable. They see some C code with pointers and bit shifts, and they're like, "Oh my god, what is?" Yeah, you are not familiar with low level programming, and that's not assembly. It's not that hard. C is not that hard. Come on. Sometimes I have trouble with complex C++ with classes and templates and inheritance. That's the thing that I have much harder time to read. I have much easier time to read pure C. And I guess that's the other thing. If I was super familiar with object-oriented programming, it was my second nature, then I would find the modern programming much easier and faster to read and maintain than the old C code. I don't look at C code, and it doesn't. It looks very familiar, and it's direct. You see the algorithm. You're like, okay, I'm gonna work on the algorithm now. It's simply there are less abstractions. But my thing is, I'm not saying this is bad, this is good. I'm not saying you can use this clean code. That was the argument. We can use the clean code for parts of the code that are not critical. And okay, I get it. Although there are some traps there. So Uncle Bob will say, no, you can find places in the code that you need the performance and places that don't necessarily need the performance. I'm just gonna talk about. Let me find it. Now this video is very chaotic at this point. And they go back and forth. He's saying, Bob says, most program. The vast majority of software systems require less than 1% of modern processor power. So why not use that in there? Yeah, but I would say the programs that create the problem, the applications that are slowing down the major application that are like, why are all these important tools are so slow? They are not the ones that take 1% of processor power. If it was that if you have an application written entirely in Python with clean code and stuff and not caring about performance, it's I don't know, a tiny widget that does nothing, I wouldn't even notice. I wouldn't even, and Casey Muratori wouldn't even be ranting. Now Casey goes and says, what about Visual Studio, LLVM, GCC, Microsoft Word, PowerPoint, blah blah blah? Those are all big applications, and they affect performance. And then the counter argument, if you have a small application, a very tiny, maybe a tool that has command line and convert some data to something else, a tool that you run on the command line in Linux or whatever. Those things are so small that they are written in pure C, they are written in Python, it doesn't matter. But those are not the ones that makes you pull your hair. It's the big application. But now, the small application, because they are so small, you could write it in C or whatever. You can do unclean code. You can do basic code without object oriented, without templates and stuff, because it's a simple thing. You don't need to overstructure it. But those big applications, because they become so big as projects, maybe there's the argument, so there we need to abstract them more so that it's maintainable. You know, if there are new programmers coming, it's not going to be low-level horror. But then those are the ones that are affected, and those are the ones that we are paying attention to. I want to stay. So interesting. Bob is describing the software in. You have some software where there is an inner loop. He calls modules. Like there is a piece of code that it's critical. It has to run fast. So this is the module that has to perform with nanoseconds. Then there are microseconds. He does that distinction. Less important for performance modules that they can be a bit slower, and the milliseconds. Maybe a button that opens a preferences window and you just check some options and it doesn't do much. And he says, that's a funny thing I was thinking. I have an unimportant module is doing so little things that it doesn't matter if it's unoptimized, because you won't see it, isn't it? You won't see it. You can write that with clean code, you can write it in Python, or he prefers something called Clojure. I don't know what it is. I just want a simple language to write algorithms personally, and C is fine. I'm living in the past. So he says, there are modules in the software that they are doing nothing, so those could operate slower, with the response time approaching a second. But now this is an oxymoron, because if you have a module that is so simple that it does nothing, it does very few things, so it doesn't need to be optimized, why would it approach a second? What is the thing that it would do that it would approach a second? If you have a form where you type a text, you want to press some keys and it takes a second, and the user says, okay, but it's an oxymoron, because if these modules are not in the inner loop, they wouldn't take a second to finish. With the worst code possible, they will still be fast enough. So it's an oxymoron to say, oh, those that the response time approach a second is the modules that we don't care. But you wouldn't see the second if it was. It's hard to explain. That module that is outside of the inner loop, that is somewhere outside, that happens. That runs so little that even if the code goes horribly, you wouldn't notice the performance change. Then why would it be a second? And here is my other point now. I thought at that point, like Casey is doing some comparison about how many cycles are wasted. Do you know what does a second mean in modern computers? I have this Intel i7, I don't know what's stepping. I'm confused by that stuff. 3.4 gigahertz is running. So it's like 3.4 billion cycles in a second. What is the thing that would need 3.4 cycles in a second? Do you mean how many? And if you can run more than one instruction in a cycle in this model processor, I can think of, back in time, I was working on the Amstrad CPC, and where you Z80 at 4 MHz and so on, and it happens that it's obviously it's 4 million cycles, but for some reason, the smallest Z80 instruction takes 4 cycles, an open instruction, and on the Z80 on the CPC, the way the hardware is synchronized, this is different on the ZX Spectrum, but on the CPC, the rest of the instructions are multiples of 4. So it's 4 cycles, 8, 12, 16. There is some instruction that would take 11 cycles, but on the CPC it takes 12. Okay, so I like to count in NOP cycles on the CPC. And this is the exact amount of NOP cycles. And I think if you divide this by 312, yeah, these are the vertical scan lines on the, even outside in the border. You have 64 NOP cycles per line. And this is in 1/50th of a second. Okay, so multiply by 50, in 1 second it would be like 998,400, almost a million NOP cycles, or 4 cycles. But we use on the CPC, when we want to, how many cycles I have per pixel to do this rendering effect. We use, if you want to postulate, you wanted to do a tiny 64 by 64 pixel, some rotozoomer or plasma, some real-time software effect for a tiny 64 by 64, 4096 pixels. So we would divide, I would do that and postulate. Oh my, I have about almost 4. Say 5. Maybe I also have the music player and other things in my demo, of course. So if I only have 4 instructions per pixel. I have to do calculate the effect, grab a left and right pixel to create the byte because of the video RAM structure, find the video RAM address. So maybe you go linear in a line for a pixel per pixel effect. I have to do so much stuff, and I have to do them in 4. And you cannot. Usually a 64 by 64 effect will be 25 frames or 17 frames at 3 VBL, 3 vertical refreshes. Okay, usually with the fastest code you can think. Or I used to. I want to do some sign dots or sprites. Could I do how many theoretically how many cycles I would have for 256? Okay, 78. Maybe we can do some 256 signs, but you also have to delete the signs. We have to find the coordinates and y, and then I would write code and I would see. Okay, that takes 24 cycles. Maybe I can fit it. And what I want to say, and that was the amount. And then I said, wow. Imagine if the Z80 was running at 16 megahertz, or there is the EZ80 processor at 50 hertz, and much less cycles. It might be approaching one cycle per instruction, if I recall. And you're suddenly like, I don't have this, I have this, or I have, I don't know. Oh my god, so many cycles per screen, divide by 496. Oh my god. About that, or maybe a bigger screen. 120. I could do a big effect, and you were obsessing with that, and you would be, look how many cycles, but maybe I can do things for several pixels. Several pixels. If I push it. And now we don't have that. We have in my 3.4 gigahertz computer. Is this 3.4 billion? Okay, and maybe I want to do something at 50 frames per second or 60. I have 56 million blah blah blah. 56 million cycles per frame. And this is a big run, but I think you got the point, but I just want to run. It's, you don't understand, it's enormous. And maybe I want to do something in 1080p. I still have 20 to do software in 1080p, 27 cycles. And here it's at least, for most basic, it's at least one cycle per instruction. Or and it could be many instructions per cycle. And we haven't gone I haven't gone in SIMD, I haven't gone in multithreading. I think this chapter is about the many instructions in a single cycle. It's modern processor that can do more if an instruction is not using the result from the previous instruction. And he's doing some weird stuff. You wouldn't normally split your sum into. I didn't know this would have a better effect though. Because those are 4 different variables, maybe they are split in different registers, I don't know. So the next one is not a thing from the previous. I would just do the simple sum and stop. And maybe it's pretty weird for a modern code, for a simple sum, to split it into 4 variables. And there's multi-thing, there's... I'm just writing numbers, but when you are coming from an old computer and you were counting, you know these were your cycles. And they weren't little. 1 million knob cycles or 4 million cycles on the CPC. 4 million cycles, but the smallest instruction would take 4 cycles anyway. So at best 1 million instructions in a second. Is this 1 MIPS? At best 1 MIPS. It's way down from there. And when you compare that with what we have today, and we talk about we might have a less critical module where we can allow the response time to approach a second. First, if it's the less critical one, it's so uncritical that you can write bad code and still not notice it. Why would it approach in a second? Then you would notice it. You would click a button for a simple thing and you will see a delay. You say, what the hell, I'm not doing anything. Then it's way worse. And secondly, think in a modern PC how many cycles a second carries. If I had those cycles on the CPC, if I had 1,000th of those cycles, then I would be like, did I say it correctly? 1,000 of 3.4 billion is still 3.4 billion million. Okay, I'm confused. It's that. I would be like, so many cycles per pixel! Imagine the rendering I could do if I had 1,000 of that. Actually, I have 1,000 of that per. Yeah, because these are gigahertz, so from 3.4 gigahertz to 4. Okay, if I had 100 of that. But remember, this is much more than that in real instruction throughput. If I had the 1,000 of the real instruction throughput of this thing, I would be delighted how many things I can do per pixel for several pixels. And now you tell me that. All this thing for that. This thing made me think various things. Okay, it's a low module. Why would the response time approach a second if it's a module that is so uncritical that it's not in the inner loop? And why would it take a second? That is an enormous amount of time for a processor, for a modern PC. So and it goes. It's mostly, they don't say much. There's the thing that, in the Agile Manifesto, we could design it because Casey says, yeah, but if you start not caring about performance, there you design something that it starts like uncritical, because there are various places where like this is not a critical thing. I'm gonna write it like this and quicker. But then when it scales up, you have a problem. He says you don't realize that performance is lost till you realize it, and it's too late. In LLVM, when you try to build some truly big program like the Unreal Engine or Chrome, and he said then the assumption is that the performance problem will be isolated parts of code. The critical module. But the thing with these things is we don't realize. I might write something in a modern programming language. That something might be stealing with layers on top of layers on top of layers. It might be stealing a lot of cycles, but because I'm doing something small. I'm doing something small here and there in different modules, as he said, this module is not critical. Okay. But this adds up in the future, and it might be running fast. You say, hey, it's fast. My code is fine. And I'm not saying you should definitely write like this, because people prefer different things. Most people don't like to write the way Casey writes, or they don't like the low level C. And there's a lot of negativity, like, oh, these things are things of the past, and even the method, the optimization method, a lot of things are considered archaic, and I don't like this. But I'm not saying that, but there isn't even awareness. The thing is, there are two things. It's the dogma. People are negative. If you go and say, I'm gonna go low level, and I'm not saying assembly, just writing things in C. People are like, oh, are you out of your mind? You should write with clean code, and you have to use that. You should get away from the past, and you should not code the old way anymore. There is some negative dogma, like people are discouraged from, I don't know, coding like Casey wants to code, or like me. I just want the simple language and the algorithms. I don't like all this extra clutter. Sorry. So there's this discouragement, and then people don't have awareness. They think compiler is magical, it optimizes everything. They might write something that they think this is as fast. They think that this is as fast as it gets, but it could be 100 times slower. And maybe you don't need to do the crazy hacks. You don't need to do the crazy optimizer hack, but you could do some simple things that are still inside the clean coding paradigms, but do it being more aware. And okay, Bob says, yeah, but I would say in my agile manifesto we will architecture and design things to prepare for the cases of bad performance. Like it will take care of that stuff. Yeah, but it's not what happens. You have all this program and everybody is not aware anymore how much fast those computers are, and everybody is adding code. They're going by the book. This is the right way to write things. Clean code tells me I should do that, not realizing, and it's going to be fast because compilers are fast, and it runs fast. With my simple example of summing 10 numbers or even 1,000 or even a million, you won't see it. With this, you can write very slow code, and with this computer, it will still seem like, oh, it runs instantly, so it must be good. But when the project scales up and you add clutter upon clutter upon clutter, it's like death by 1,000 cuts. And that's a thing I think is the one. And the dogmas will make you, the assumptions will make you say, we should all code like this way and discourage people from coding that way, and it will be more clear. It will be both clear and fast enough, because now compilers are very fast, and if they are not, there will be a new processor, and it's both dogma and discouragement of the other way. And I mean, you might say even in cases, case Muratori's side, there could be a bit. You could say there could be a bit dogma, because he's like, don't do that, don't write in this clean code thing, because you are going to introduce performance traps, and you won't notice it. We don't know how much cycles are wasted. Then we see an old platform, the first Raspberry Pi, and we think, oh my god, it's horrible, the speed is horrible. No, it's a beast. The first Raspberry Pi is a beast. I have a 386, 486. They are beasts if you program them. If you push them, it's a great exercise to try and get into some retro platform. Everything will be deadly slow if you write them the way you write them, and learn to optimize for a retro platform. Try your best. And also, finally, Casey is making a point that, look, exactly that. Things are going so slow and we don't realize it because we have this. It's okay, we have to write things like this, don't care, the compiler will do it, we have all this layer, but it doesn't matter. Oh, where is it? Sorry. Was it? Yeah. And he says, here on the GitHub, on this whatever that is, I didn't know you can chat in GitHub like this. I'm typing and suddenly it goes slow. I'm typing. What's going on? Whoa, is it frozen? Whoa. It's like, that's my point. And do you know what that was? Okay, I think it's also the layers, but they found out it's the freaking emoji picker. The freaking emoji! I hate emojis. Why is emoji a thing? I don't understand it. I think it's some Japanese thing too. I fucking hate those cringe, wholesome, feel good. Haha, I can put emoji now in my tanks. But it was the way the emoji was parsed. In every character, it was looking back through the previous characters to see if you type an emoji, something like that. And they say, now here is my other point. And how many was this paragraph? 200 characters. It wasn't big, was it? They say maybe it went from the character you are back to the beginning. Maybe there is a bug. I don't know. If you have 200 characters and in those modern computers with such crazy cycles, even if you do some horrible code, I don't think you would be able to make it that slow. Or is it both the algorithm and all the layers of Java? How is it possible? For few characters in a box. So even then, you know, pesimization, making your code horribly slow, never ends. I've learned of that. Also, optimization never ends. It's infinite. Both sides are infinite. And I will tell you why. There are two things. There isn't. I remember that chapter. There ain't no such thing as the fastest code. This is also my experience. First of all, they tried. I think in an 88, in that system that Casey Moratori is doing instruction decoding and so on. I think it was that computer back in the days with Michael Abrams. They tried to write some, I don't remember, a text, a program that reads text and tries to count the words, and it would do, I think, it would do. They optimized it so much that it would do not 100, it would do 1,000,000 characters per second. In a second, you would have a big text with 1,000,000. Maybe I'm exaggerating. Say it's 10,000. And this is a paragraph with 200, 300 in a much faster computer, and maybe it's doing something unoptimized that to check the emoji, it looks from the character back to the beginning. Or maybe a bug. So these people, and you might think, okay, it's slow, the algorithm is bad. Even if it was bad, you are not doing it in 1,000,000 characters. You are not doing it in 10,000. Even then, even with some bad code, the waste is unless there is a bug that loops for 4 billion 32-bit goes to overflow negative from minus 2 billion to 2 billion in the 32-bit space. I don't know. And modern computers can do that very, very fast. They can loop through 4 billion integers and finish, I don't know, in a second or a bit more, but and this is 200 characters, even if it is a case of a bad algorithm. People would optimize. I think those were running on the 8086, not 286, not 386. And someone wrote code that did 1 million. That's the first thing. And you will think that if you see this and you see, okay, I guess character scanning is slow, and I tell you, okay, someone on the 8086 with 4.77 megahertz wrote a code that would count words in a text that is 1 million characters in a second. What do you say? You would see this and say, if this is that slow, then what you are describing here is physically impossible. It's like you are telling me I travel 10 times the speed of light. We know you cannot travel over the speed of light. You cannot even approach it. So what you say here is fake. It's a hoax. But only if our perception is skewed by how bad the software is today. If you have optimized this, if you have seen, you would think, okay, here in modern computers, these computers are a beast. This can be. That's the one thing. The more, if you see how old computers were, the software, if you try to code for an old computer, and then try to do your best to make things faster, and you see at first it seems impossible, but then maybe you can read some tricks though. Maybe you have to see what other people do. And it's a process that might take months to learn, or even a year. You know, this is what I'm doing with the retro demo scene and all stuff. Your mind expands. And you know that Case Muratori has right when he says the waste is enormous. It might be 1,000 slower code than it should be. And that's the second one. You also learn something else. People think optimization, sometimes it is like that. Like, you are going to write things in assembly and you will get 10% faster or 30%. Why bother? It's not even in assembly. You can be in C, in Python, in whatever, if you have the right mindset. If you don't think that's how fast it is, computers are slow. If you realize that if you see this and you're like, this is wrong, it can't be that fast. Something is horribly wrong here. If you don't see it, you will think, I guess text parsers are slow. It's not a fast process. That's what my good. But if you know that it has to be much, much faster, it can't be that slow. You open your mind, you expand your mind. And there's another thing you expand. Optimization can be, you can make something being 10 times faster, 100 times faster. You can, if you wrote in low level C and assembly, you could still make things run 10 times faster in some cases. Sometimes, okay, you hit the head, but sometimes you feel, that's the point, that's the other point of this article that I like. You hit. So, Terje Mathisen, he made the fastest word count. He thought he made the fastest word count. He says, I have the fastest code possible. If you ever do magic voodoo, you will get a 5% speed up. If you tell me you did it faster than that, it's like you are telling me I went beyond the speed of light. It's impossible. And then he did double the performance. And then Abras, I think someone did the code in Pascal, Abras ported it in C. It was even faster. And then he posted it as a challenge, and Abras thought, okay, I think that's the fastest. You cannot do anything more. And people do 3 times faster. 3 times, not 10%, not 20%, 3 times. 3 times by 3 times by 3 times. You might code, even in the retro. I have coded things in the retro with my extreme optimization obsession. I have coded things that are like, okay, this can never be any faster anymore. It's over. It's over. I hit the limit. And then later, maybe a year later, maybe a month later, maybe the next day, I have some new ideas. I rewrite this thing. I see it. As he says, truth to tell, I didn't expect a 3 times speed up. Around 2 times was what I had in mind. Which just goes to show that any code can be made faster than you'd expect. If you think about, that's the thing, think it long enough and from many different perspectives. I revisit algorithms, I revisit from the algorithmic level to the low level assembly level to the C level to other kind, from the data structure level, from different techniques. Some demos in code that is like, okay, this is 1 frame per second. This is slow here. Maybe I can go 2 frames per second, but don't expect it to go 10 frames per second on a 286 or something. And then I make something that is 15 frames per second, and there is potential, because I noticed other things that I can do in the future. Some of them are hard work, and I leave it for the future. And I always revisit stuff, and it's like it's infinite. Of course, it's not infinite. There is a limit. It's not magical. It's not paranormal. But there are times when you write something that is slow, and then you see a demo, and someone has made the same thing running 50 frames per second, and you are like, how? My code runs 2 frames per second. If I double the speed, which is very hard, it would go 4. How did he run it 50 frames per second? How? And I get that. I'm ecstatic because this is the magic. This is the thing that motivates me to do all what I do. And if you do it in all computers, there is some excitement. It's an expansion of the brain. I become ecstatic. And there are points where you might have written the most low level, the most assembly, the most cycle, everything, and algorithmically state of the art in every aspect, and you think it can be faster, and then you do it faster, someone does it faster, it's not 10%, it's 3 times faster, it's 10 times faster, and you're like, how? And you think you reach the end. And that's the thing, in the modern time, we reach the end. We write an ad in JavaScript, it creates that, and you think it's an ad, I can do it. It's not a complex algorithm. That's what it is. It's a sum. And even when he writes it in C with an ad, he's doing a lot of other stuff, especially the instruction per clock, and then the other are obvious. Okay, if you do it simmed, and which is fine to do in a sum with sim, but it gives. And I think he went to almost 14 ads per cycle at the end. And that's what I mean. So it's another optimosophy rant in a way. I don't know how I will name it. And they say if you put this symbol, because it separates the emoji, the search stops and it searches from here to here for an emoji, and then things go fast, and I had so much fun, and Uncle Bob was laughing about it, and now it stopped here. I don't know if there's more. Yeah, I'm more of a Casey fan. I like Anglebob. General, I'm not into the design, software design and stuff, but I don't dislike any of you guys. I'm just, and it's interesting because even Bob says, I'm not a new program. I started in the 70s with C and assembly, and I was a hacker back then, and I created this with VI because I'm really not a C hacker. It's just that it's two different directions. I'm really obsessed. Whether it's good or bad for me, I'm coding for myself. I mean, in my job, I'll go whatever other code guidelines. But at home, I like to write I like to optimize things to end, and it has expanded my brain. And I like Case's content because he also says that he expands the brain in another way. I expanded my brain in what is possible, especially when I'm programming on Retro about optimization is infinite. It never. You think you reach the end and you can make things faster, amazingly faster. Now he expanded my brain. Although I was guessing that you can't believe the waste that is happening in not just Python but all the software, especially the script languages and the web programming. But even in C and C++, if you don't know what you do or if you're using modern stuff that are more pushed, while the old ways is discouraged and they tell you, you don't need to optimize, it's all right. And that's it. By the way, this is very unoptimized. And the linear is 0, but I'm also doing divisions per pixel, and I'm calling a boot pixel because I wanted to learn the video RAM of the Virtual Boy. But I know it. Okay, my earliest example is to work how the Virtual Boy works. I'm not saying the first codes I write is optimized. I might write things faster and make things work. I might write some unoptimized things, but I'm aware. I'm aware that there is more than that. I think this is 640 stars. If I put a bit more, it goes half the speed, and there is flickering on the Virtual Boy, which is not good for the Virtual Boy especially. And that's it, guys. That was my big rant. I will see in the future if I'll post an Opti news or something else. I just need to finish working with something. See you.